when you have a kindergartner in your house, she won't let you forget to not wear green, right? Because, you know, St. Patrick's Day is like a big deal in elementary school, right? Especially kindergarten, you know, because the leprechaun comes and like messes up your classroom and all that jazz.
Stinky leprechaun.
Okay, so with this idea of entropy, there's a few ways you can think about it. Once again, it is kind of an abstract thing to wrap your head around, because like enthalpy, heat, right? Like you can understand heat because you can feel it, you can see it. We can measure it directly with a thermometer. There's no thermometer for entropy. It is a measured value, but it's a much more complicated thing to get to.
It's a probability?
Yeah, it's a probability measurement, but it's an actual energy unit. So the units of energy, the unit of entropy has joules in it, just like delta H is joules or kilojoules. It is a value of energy, but it can be harder to understand because, once again, it's just more abstract. The idea of it, once again, is another way you can think about it is the disorder or organization of a system. A system that is highly organized has very low entropy, while a system that is very disorganized or spread out has high entropy. So we would say that this has like, from going from here to here, we'd say that the entropy change is positive. Entropy has gone up, or delta S would be positive within that change. On our case, we're going to be focused on the molecular level view, right, of what are molecules doing in terms of their entropy. Yeah, Spencer?
What does that one say?
Oh, the one right on the line? I don't even remember. Oh, free. Good question. When they land right on that bar, it's like, I don't know, it's very hard to read. But yeah, so the freedom of their movement is another thing we can look at. You can actually blame entropy for your messy room, because the second law of thermodynamics states, as the video talked about, is that the entropy of the universe is increasing. So it's interesting because in the first unit, heat, right, is conserved. If something gets colder, it's because something else is getting hotter. The entropy is not that way. The entropy of the universe is constantly increasing. In a sense, we're heading to infinite chaos. That's what it tells us.
Yippee!
The scientific law. But like, you can kind of even see it in your daily life, right? I mean, entropy happens to my desk on a daily basis. Every day I start my day off and my desk is very organized, very clean, and then by the time you guys come in right before lunch, it's always like this.
As things happen in the universe, naturally entropy increases. Kind of like how if you don't clean off like your computer desk, eventually it'll just get stuff building up on it.
Exactly, yeah. What do I have to do in order to combat this? I have to do work. So entropy will naturally happen unless work is done to a system. If I do work to the system, then I can control the entropy. But if not, it just will constantly keep growing, right? And in terms of the spectrum of the universe, we can't do enough work to balance out the chaos that just exists, right? Sorry if that was like depressing. It's not meant to be that.
But is it like entropy increasing at a rate that you wouldn't really be noticeable to the race, or is it like actually kind of like?
That's a good question. I don't know. I don't know if they've been able to like graph, like, is entropy getting faster? Like, is it exponentially going at this point in time?
If they were, I mean, they probably weren't, but if they were able to somehow measure entropy back in like the Renaissance,
Yeah.
you notice like a big change?
I don't know. That's a good question. I would say it's not a linear progression.
It's probably exponential.
I'd say it's more exponential because as you develop more, then more chaos ensues, right? Like, but that's a good question. I think so. So looking at this equation here, everybody, this has a negative delta S value. We'll talk about how we get there. But this reaction, as it's written, has a negative delta S value. So when you're trying to predict whether entropy is increasing or decreasing in a system. Now, entropy always increases in the universe, but for a single system, entropy can go down or it can go up, okay? In this case, what we're noticing is, once again, that ability to move and how much movement you have. On the left side of the arrow, I have 3 molecules separate from each other. But after the reaction has happened, I'm now down to 2. The less amount of things you have, the lower the entropy because there's less dispersion, less freedom of movement.
Do you think of it kind of like pressure? how like less molecules is less pressure?
Yeah, it actually has a similar idea of how like we compared moles like with the Le Chatelier shift. It is very similar to that, Tyler. Yeah, good connection. I never even thought that before. But it is similar in that sense of when you have less things, right, then there's less chaos that can ensue, right? Less movement, less dispersion, okay? This kind of just shows you in a visual side of things, right, that the formation of these new bonds decreases its ability to move. So the more you bond something, the less entropy it will have, because bonds limit movement. Or the greater freedom something has, the more entropy there will be. So we're going to look at it from the side of, once again, molecular view, how atoms can move. Okay? So as you're writing that down, so we have this thing known as degrees of freedom. Is kind of another phrase you often hear when talking about entropy. And the more degrees of freedom something has, the higher its entropy. The less degrees of freedom, the less entropy. Okay? So, what is the main, how do you describe the movement of a solid? Good, they don't move much, and how do they move? Like molecules in a solid, if I could see inside your table, yeah, shake or vibrate is the common phrase we use. Now, we're going to expand that from what you maybe think of vibration. Most people think of vibration like, yeah, like what your phone does, just like, right? But in terms of a molecule, it's actually kind of cool what it means when we say the word vibrate. Vibrational motion is in relation to the bonds themselves. That the bonds within a molecule can move, and those are what are vibrating. Now, as we go through this is going to be, you can all take this, and I won't, like, it's not copyrighted. But you can take this dance I'm about to show you, and I'll do it at prom, and it's going to make everyone be like, the new coolest thing.
All right.
Are you ready for this? Okay. So solids do what type of movement? Only vibrational, right? So they can do bending. Okay. They can do symmetric stretching like this. Okay. Or they can do asymmetric stretching.
Wow.
Okay. Thank you. It gets better. Just wait. Because when you turn something to a liquid, you now have more freedom because you're not like rigid, right? Like solids, they're more rigid. But when you add in a liquid, they now have the ability to rotate as well. So they can do vibrational while doing rotational, right?
In like water?
Yeah, like so water molecules have that ability to spin at the same time as vibrating. When you then become a gas, you now have even more freedom because you're not like side by side. True. I'm gonna go side to side but like they can do vibrational, rotational, and translational all at once.
Do a cartwheel while doing
Wouldn't that look cool at prom? Like everybody all at the same time.
That looks like something like Jackie Chan.
What did you say?
cartwheel while doing symmetric stretching.
That's true. If I want to get really fancy, then I can go like horizontally and up and down. But imagine, like literally though, imagine everybody at the dance doing all three of those at once.
That'd be amazing.
Like,
It'd be like molecules.
but like entropy is like crazy. Like how chaotic would that be? Right? And that's why like gases, their entropy is crazy high. Right? But then the more you limit those, if everyone was just a solid and was just standing in place doing this, right? Like still pretty cool, but like definitely way less chaotic, right? Like you wouldn't be taking people out as you dance.
Oh my gosh.
I guess if we were like in unison, then it could look quite cool. So once again, zooming out from the bonds, solids do vibrational, liquids do vibrational and rotational. They can also technically do translational, it's just more crowded, right? So they don't do it easily, but then gases can do all three. Okay, so that's what we're going to be looking for when we're trying to identify is entropy increasing or decreasing. A key part is phase changes. If the phase is changing, that's going to affect entropy a lot. Okay, so these are the three things we're going to look for. Really, 1 and 2 are kind of the same. But if a liquid or a solution forms a solid, then that means, or they formed from solid, sorry, that means entropy is going to go up. So So anything you take something from a solid and either dissolve it to make it aqueous or melt it, entropy is going up. Okay? The second one says gases. That's what that weird word is. So if a gas is formed from something that was previously a solid or a liquid, entropy is definitely going way up. These ones always come first. Look for phase changes first. They like dominate the entropy game. But if phase change isn't happening, then you can look for the number of molecules. Where if the number of molecules increases, entropy is going up as well. Xander, did you have a question?
No.
Okay, for now. Okay. Any other questions on entropy before we try a problem? Okay. With your table buddy, I'll give you like 2 minutes. You're going to go through each of these examples and say, is delta S positive or is it negative? Ready, set, go. Or no change if you want to claim that as well.
Oh, that would be positive. Think about it. They have more freedom to move around. That's more. This one is negative. No, I'd say it's there's less singular molecules in there. No, because N plus O makes NO. No, but I'm saying NO creates a finger. I'm not, you know what I mean though, right? I'm saying, yeah, but the molecules are bigger, it's like more acidic.
Set your pencil down if you're done thinking. That way, just know you're ready.
Yeah, I just figured. There's one more electron.
Okay, as I go through them, point up if you said entropy is increasing. Point down if you said entropy is decreasing.
What if it's no change?
Or sideways if you think it's no change. Up, down. Okay, A. What's going on there? What do we think? Show me with your finger. Oh, well done, everybody. It is definitely increasing. Have a smiley face for that. Oh, you need those back. Some of you.
Oh wait, I don't even have one.
I have some of those. I just remember.
Can I use this paper? Mine's like heat up.
Yeah, I have some extra left. While I pass these out, just to make sure we got it, why is entropy increasing?
Because you're gonna be a gas that's spread apart.
Yeah, phase change, right?
Wait, Alvisa, are we gonna do the multiple choice?
Yeah. Yeah, so we'll finish. We actually have like one more thing after this, then we'll be done. Yeah, so we should be, my plan is before, are you going on the bus today? Oh, you're not, okay. Wait, are you going on the bus today? So we should be done with the lesson before you have to leave. That's the goal. The track team is, I got some of those. Why can't I find it? Oh, I know. Brian. Okay, come on the next one here. Point with your finger. D, increase or decrease? What do we got? Well done. Decrease. Have a smiley face. C. Good. Very good. Also decrease and D.
Oh wait, no.
Now, obviously this one is tricky. And it's, I've never seen them do like these tricky ones that like appear to be the same but aren't. But it's actually pretty rare for entropy to stay at 0. and not change at all. So it does actually decrease. Somebody who said decrease want to share their logic of why? Tyler,
I
go ahead.
thought because it's changing from two of the same atom to like clumping together with an oxygen, and that kind of decreases the clutter a little bit, makes it a negative entropy. At least that's how I think of it. But
You're on the right note there. Lily, share, and then I'll tell you why you're kind of right.
I just did it based off of the third one of how it says the number of molecules of gas increases during the chemical reaction. So like it starts with gas and ends with gas, then I figured like if it's still like the number of gas still increased in a way.
Oh, okay, because like them being spread out. Somewhat, it is tricky because technically there are two on this side and there are two on that side, but it's like two of just different things. What's your thought, Sandra?
I was gonna say just like there's two and then there's one that's combined. I mean, there's the same number of molecules, but I feel like
But they're now
to me it
all
was
the
just
same.
more ordered in the 2NO.
Okay, versus like a mixture of these two things, now it's just one thing. And that's kind of part of it too. Did you have something?
I was gonna say this is
Yeah, there's kind of a few ways to think about it. One, you think about that of like, in a sense, these two together are like a mixture. This is actually a pure substance, right? A compound is a pure substance by itself. Going along with what Tyler said, it's actually also in the sense of, now that they're bonded like this substance is polar. And polar things next to other polar things naturally do what? Come together. And so even though it's a gas, these would be more prone to being, but once again, I just threw that one on there just to get you. So questions in general, I'd say if you didn't understand this one, you're okay. The questions on the A, B, or C. Okay, so that's the first part of your homework tonight, is I give you an example, you tell me, is entropy going up or down, okay? Second part of it is calculating it. So there's a calculation for entropy based on entropies of substances. So scientists have already determined mathematically the entropy of individual compounds. So if you ever want to know the entropy of a whole reaction, we can compare how much entropy was there in the end versus how much entropy you started with and know the net entropy change. So it's a very similar equation we've done in past units of products minus reactants. This is on your formula sheet, by the way, so you don't have to memorize it. And the other thing too is they're always going to give you values. Otherwise, like, it's impossible. Okay? So if I want to find the entropy for this reaction, we're going to do products minus reactants. So my product is 2 NH3s. So I need to do 2 times 192.5. And we're timesing like 2 moles of it by it because of the balanced equation. Okay, so these are my products. And then we're going to subtract all the reactants. So we have 1 N2. So we get, in a sense, it's like 1 times 191.5 joules per mole Kelvin. And then plus 3 times 130.6. So products minus the reactants should give you the overall enthalpy change of it. Questions on my setup? After that, the calculator does the work for you.
Is this gonna be on our sheet?
Yep, it is on your formula sheet. Yep, so you don't need to memorize it. I think, I can't remember. What did I get? They don't tell me in yet? What'd you get?
Negative 198.3.
Thank you, Michael. That's my base numbers out there. Okay, negative 198.3 is what we get when the calculator does all that. I would always do a quick check. Does that sign match what you would expect it to be? Should entropy be going down? going from 4 to 2 of gases, right? So it can be a good quick check of making sure you're not doing it backwards or something like that. So, questions on this? Yeah.
Is there an equation we were supposed to get for this? So there's a box.
Oh,
above this
yeah, I
one.
can be writing the equation in the box. I totally forgot. So delta S, it's just so delta S for the reaction will equal the sum of the S's of the products. We've talked about this, remember the summation sign? So this means add up all the products minus the sum of the reactants. Thank you, Ethan. I said it, but we didn't write it down. Yeah, Michael.
Why are the units joules over Kelvin in the answer, but joules over mole Kelvin in the product?
Oh, great question. So I didn't say this. So we're timesing them by how many moles there are, which in a sense like cancels out the mole. And the final delta S will always be just joules per Kelvin. So good observation though. Any other questions on this? So that's the second half of 9.1 is just plugging them in. Yeah.
Will you be provided the standard mole entropy, or will we have to find those?
No, those will be given. So yeah, because there's no way to like find them without like a lab setting. So it's also kind of a nice way that if you see a problem and they give you a table like that, right, you should know, oh, I'm gonna plug them into this equation.
So you just have to remember it's kind of like products over reactants, but products
Yeah,
minus.
very similar. And you'll see, where's the formula sheet? We actually did a very similar one to delta H. In the thermodynamic section on your formula sheet, there's a delta S, delta H, and delta G equation that look almost identical because they're products minus reactants, products minus reactants, products minus reactants. So it's just what we're finding. Of like delta S is finding entropy, delta H is finding enthalpy, and then delta G we'll learn about Tuesday. It's called Gibbs free energy, but it's just another type of energy. So
Haven't you got the weirdest names?
yeah, it kind of does. Sometimes I feel like that's what makes it harder. You just get caught up on like what it's called. Any other questions on this? Okay, that's it for today. So you need either your Chromebook or your phone, because I'm going to pass your test back in to type in your multiple choice answers. And then Michael, do you want to get started on the test from being on last night? Does that work? So grab your calculator. I'll put you in. It's actually on paper, so you don't need your Chromebook right now. Yeah, grab a calculator and a pencil. I'll grab you a formula sheet.
Yeah.
The multiple choice is 18 minutes. If you finish it before and you want to get started on the FRQ.
Are you gonna wear your own suit, or are you just gonna wear one? Are you in them like the same size?
Yes, it actually
The C question.
3 minutes.
I didn't
Sure, you were.
Okay. What are we doing?
Test.
Test. Okay. All right. So I'm going to pass back your multiple choice. You then, I'll give you the access code. Type in the access code. Plug in your answers. Don't get distracted because you only have like 2 minutes before we'll just lock on you. 3. Oh, I gave you 3. But still, don't get too distracted.
19 minutes.
Okay. Well, the original test was, but like to plug in your answers. I know they're giving you a few minutes. And then once we get that in, you'll be able to see your score. And then I'll pass back. Oh, you need to start at 2. Let's go start yours, Miranda. Then we'll pass back to the FRQ. Grab a calculator. I'll grab the test. I forgot we were.
Why is it 3-minute time? Oh, that doesn't make sense, but still.
So I had to pull my pencils always run out of line during tests. I've done 2 math tests where at the very beginning of the test,
What are you grabbing?
it's all on paper. My pencil runs out.
I already got one.
Oh, yeah.
It's on a stack.
Normally I have a backup. Normally I have a backup. Yeah, that's facts.
Do we wanna stop the video?
Oh yeah, you can stop filming.